Okay, so we'll get started. So the we're very happy to have Peter Armitage here from Johns Hopkins University. So he received his bachelor's degree from Rutgers, and then he moved to Stanford for his PhD, where I learned he first wanted to work with Bob Laughlin doing theory, and then luckily he got switched to experiments. He worked with ZX Chen doing doing angle resolved photo emission experiments. And then he moved on and he did work eventually starting his faculty position at Johns Hopkins in 2006. He developed and explored several breakthroughs in terahertz radiation to study quantum materials and coherent phenomena in quantum materials. He has received several prestigious awards from the NSF, Sloan Foundation, DARPA, Macmillan Award, and many others. He has a very broad knowledge of condensed matter physics, which is evidenced by the fact that he has several review articles that are very influential, from electron-doped cuprates to Weil and Dirac semimetals to axion electrodynamics in materials. So it's our pleasure to have Peter here to tell us about some explorations into the Ising model of ferromagnetism. So Peter, thank you for coming.
So thank you so much, Eduardo. So that's quite loud. Turn that down, or it's okay? It's probably okay. So yeah, thank you very much, Eduardo. So really great pleasure to be here. It's been a while since I was at Yale, but nice to be back. So so what I'm going to tell you about today is about the best material realization we have of the Ising model, and in particular, I'm going to tell you about actually a particular material system. It's called cobalt niobate, in the experiments we've done on it, and I hope that telling you about a particular material won't be considered too prosaic for a kind of general audience. I want to do a number of things in this talk. I'm going to tell you about the Ising model, and it's been at the forefront of quantum and classical statistical mechanics for over 90 years. But I'm also going to tell you about the history of the Ising model, and also Ernst Ising and the small bit, the history there, but some of the small contributions that I've made to the history. I think it should be interesting for a general audience. I think it's fair to say that the historical developments of Ising's model show a disregard for traditional academic boundaries. Physics, metallurgy, mathematics have all been involved. Some of the most recent applications, of course, of Ising's model have been in biology. The most striking success of theoretical successes involved with the Ising model involved such challenging mathematics that it stumped all the physicists that attempted to solve it, and it had to be solved by a mechanist, albeit one of particular mathematical capacity. And it brings to another point is in reviewing my slides for this talk, I realized that there are many connections to Yale. In fact, names like Gibbs and Onsager and another will come up throughout the talk. So when you look at a quantum version of the Ising model, what's the matter? This thing is bouncing around here.
Here, it's,
Yeah.
so that's it.
Better? Yeah. Okay, good. Oh yeah, much better. Yeah, thank you. So when you look at a quantum version of it, it's still the simplest example we have of quantum criticality, which is an aspect that's still at the forefront of condensed matter physics. And I think it's amazing and as simple as the system is a one-dimensional chain of spins, analogies to phenomena and mathematical structures as rich as core confinement, quantum number fractionalization, Majorana fermions, Airy functions, 248-dimensional Lie algebras can all be found. So I want to do a few things here. As I said, I want to tell you about the research we've done, but if I have one real goal in the talk today is to give you a feeling how condensed matter physicists like myself go and try to look for simple and emulate simple Hamiltonians in real materials. So the particular material I'll tell you about, cobalt niobate, was first discovered in actually a class of igneous rocks. It's a mineral, and it's challenging, right, to start from a little black hunk of something, which literally could have started its life blown out of a volcano, and in the end, kind of come up with a systematic understanding of it and kind of look for beautiful universal physics that we're interested in. Okay, good. So so there's cobalt niobate. It is a mineral, as I mentioned, and well, another connection to this bit of the world. This class of minerals that we call columbite, columbite or Columbus, was actually first discovered in a Puritan farmer's field in Essex, Connecticut in 1605. The rock was sent to the Royal Academy and it sat there for 200 years before people had the sense to look at it and discovered it was a new class of materials. There's a cobalt version and a zinc version and a nickel version and an iron version. We're talking about the cobalt version. That's what it looks like in the Natural History Museum in New York City, a few centimeters wide. This is what the crystal structure looks like. It's these edge-sharing octahedra that I'll tell you about later. This is what it looks like when it's grown in the traveling solvent floating zone furnaces at Johns Hopkins University. Not as big as the volcano grows it, but hopefully of higher quality. And that gives you another feeling for the crystal structure right there. Sorry, did I miss a slide in here? No, okay, good. Before I get into it, let me thank the various people that made the work possible. So first and foremost, my former postdoc, Chris Morris, my colleagues, Oleg Chernyshev, Tyrell McQueen, longtime collaborator, Bob Kava, colleague at Johns Hopkins, Syed Kopaya, various postdocs and students who have worked on generations of this, my former postdoc, Rolando Valdez Aguilar, students of Bob Kava, student of Oleg Chernyshev. At the end of the talk today, I'll tell you about a very productive collaboration I had with Ribu Kaul at the time at the University of Kentucky, but now at Penn State. It was actually the last colloquium or talk I gave right before COVID hit in 2020. And at the end of the talk, we would usually talk about things that I didn't understand about the data. And Ribu and I got to talking afterwards in about 30 minutes, hashed out the big picture that solved a lot of those other problems. And also a collaboration with Thomas Room and his group at the National Institute of Chemical Physics and Biophysics in Estonia. Okay, so I give you my conclusions in advance, so when I invariably run out of time, you'll have seen them. I'm going to tell you about the what and why of Ising's model, tell you about the history of the Ising model, so Ernst Ising and beyond. And as I mentioned, I'm going to tell you about cobalt niobate, which is the best material realization we have of a one-dimensional Ising chain and the interesting physics that in it. I'll tell you about the various kinds of experiments that we do, which is called terahertz spectroscopy. And here there's interesting physics in the system, both when we just take this material and cool it down. And here there are analogies to quark confinement in nuclei with the domain wall confinement that happens in the system, and exceedingly rich spectroscopic structure that comes out. And I'll tell you a little bit about what we learned there. And then I'll finish up by telling you about where we are now with this system. The one-dimensional Ising model, in what we would say is transverse magnetic field, is the best example we have of let's say the simplest example we have of a quantum phase transition. So I'll tell you a little bit about the work that we're doing there. Okay. So there it is, the 1D Ising model. This is in the simplest nearest neighbor case. And so you just have some kind of binary variable that interacts with the nearest neighbors. There's two degenerate ground states, right? All the spins can be up or all the spins can be down. Whoop, excuse me. Can be down in the ground state. We know from Ising himself that only in the one-dimensional case, only zero temperature is there any long-range order, but higher dimensions have long-range order, finite temperature phase transitions, and that's something, if you will, that Ising got wrong in his original paper. There he is, Ernst Ising, first page of his PhD thesis in 1924. And a picture of him in 1925, shortly after he wrote his one paper on the subject. You only have to look at the original paper to know that the problem was given to him by his advisor, Lenz. Many authors call it the Lenz Ising model. I call it the Ising model just because it makes my story a little bit better, if you will. Ising intended the model to be a good microscopic model for magnetism. And this is essentially the story of my talk. So it's not that. It's, one can say, much more than that, and also less than that. 1924, Ernst Ising graduated from the University of Hamburg with his PhD thesis and showed that there was no phase transition in one dimension and argued the same thing was true for higher dimensions. In 1925, had published his sole scientific paper on this particular topic. And I think it's fair to say that the history of the Ising model is long and winding. And even when there were complete results, they were long in coming. The grand significance of them, I think it took a long time to be properly appreciated. For instance, the notion that near phase transitions, that there are universal aspects of phase transitions that come out independent of the particular physical system. This took quite some time. And I think among other things, what it shows is that there's really more to physics than just studying, some particular physical problem and solving it. You really need to understand how some results fit into a general context. And physics is now perhaps the search for universal phenomena, but it perhaps wasn't always the case. So the problem that Lenz gave to Ising had two parts, and both parts were impossible. Right? So that's a good PhD advisor. So first, Ising was to derive a microscopic model for the interaction of one magnetic unit with another magnetic unit. And keep in mind, in 1925, the notion of spin was basically as new as you could imagine a concept going, but they had a notion that there could be one magnetic unit that now we would call spin and another magnetic unit. So he was to derive a model that accounted for this alignment. And of course, this was impossible what they had at the time, right? This is a problem that really wasn't even attacked at all till the 1950s by people like John Goodenough, but really was in the 50s and 60s by people like Goodenough and Anderson when they came up with the notion of super exchange. In 1925, quantum mechanics had barely been invented, right? So this was certainly impossible. The second thing that Ising was to do was to calculate the full the magnetization of a three-dimensional material. And so that's also, we believe, perhaps an impossible problem. Ising had to confine himself to assuming a magnetic interaction for the first part and sticking to one dimension for the second part. The three-dimensional, we'll talk a little bit about the two-dimensional Ising model, but the three-dimensional Ising model is, of course, still unsolved. So Ising solved the 1D model exactly, got the partition function, found there was no singularity in one dimension, correctly determined and ascertained from that there was no phase transition in one dimension. And of course, a related calculation is done by most undergrads in their first statistical mechanics course. This, perhaps rendered in unconventional form, is an expression for the magnetization from Ising's original paper. That's the results of this related calculation that's done by many undergrads in their first statistical mechanics course. This is a plot, let's say, in red as a function of temperature, the energy of the system as a function of temperature, and blue is the heat capacity, the derivative of that. And you can see, indeed, there's no glitches or kinks or features that would indicate some kind of phase transition. Ising had said, indeed, no phase transition, and then had some particular argument, quite wrong, that there would also be no phase transitions in 2 dimensions or 3 dimensions. He found that this was kind of a disappointing result at the time for him. And so Hamburg was a hotbed for this kind of physics at the time. So Pauli had just accepted a position in Hamburg. Also present in Hamburg at the time were Stern and Gerlach doing their famous experiment. And Ising had intended and had hoped that his model would be a model for ferromagnetism. And as the model didn't show ferromagnetism, it was a disappointment. And this is certainly how he had considered it. You can read this quote from a letter from Ising to this historian of science, Stephen Brush, in 1967. Ising wrote, "I discussed the results of my paper widely with Professor Lenz and with Dr. Wolfgang Pauli, who was at that time teaching in Hamburg. There was some disappointment that the linear model did not show the expected ferromagnetic properties." And here by linear model, he means one-dimensional model. So Ising didn't find phase transition in one dimension, but this was a rather significant point. And this general idea that then he had that no phase transition would be found, even in higher dimension, was also important. Phase transitions, of course, have been noticed since the early days of people, early days of physics, but the early days of people. In a phase transition, something generally non-analytic let's say in a classical phase transition, happens as a function of temperature. There's some glitch in an energy or heat capacity. Generally, we believe that all of the thermodynamic information for a physical system is embedded in the partition function. And there was a notion at that time that let's say conventional statistical mechanics as conceived and understood by people like Gibbs and Boltzmann, that something was missing, that you couldn't get phase transitions from conventional statistical mechanics. And the argument was essentially that if all thermodynamic information is embedded in partition functions are some sum of exponentials, which are analytic functions, and a sum of analytic functions is an analytic function. So from this, you can't get something non-analytic that comes out. And of course, what they had missed was the significance of the thermodynamic limit. Yeah, so a finite sum of analytic functions is not non-analytic, but an infinite sum of analytic functions, themselves analytic, can be non-analytic. And so the notion that you needed in the thermodynamic limit, an infinitely large system, this was something that was not known. So the fact that Ising had shown that in one dimension that there was no phase transition, and then argued or claimed that the same thing was true for higher dimensions, this was, if you will, rather misleading. Even as late as 1937, 1938, people like Sommerfeld were claiming that for every physical state of matter had its own partition function. Right? So it took quite some time to work this out. That the notion that you could get something non-analytic in a partition function itself, this was something that needed to be understood. So if you will, of course, we've had our revenge on Mr. Ising, at least on this side of the Atlantic, because we almost universally mispronounce his name as Ising. So it wasn't until later that the idea to study the Ising model as a model for phase transitions in general caught on. The concept of the Ising model as something mathematically interesting object that, if you will, exists independently of any particular physical representation, any particular physical approximation. This seems to have started in the Cambridge group of Fowler in the 1930s. Of course, anytime you have some kind of binary variable, spin up or spin down, black or white, head or tail, you can map this to the Ising model. The title of my talk today comes from an important paper of Piles in the 1930s, and you can read right here, right? So this is the title of my talk today on Ising's model of ferromagnetism. Piles writes, the Ising model is therefore now only of mathematical interest. Since, however, the problem of Ising's model is more than one dimension, has led to a good deal of controversy, in particular, since the opinion has been expressed that the solution of the three-dimensional problem could be reduced to that of a linear model and would lead to similar results, it may be worth to give its solution. Piles goes on to say that, you can read it better than me here, come around. The solution has now become almost obvious because a number of mathematically equivalent, although physically different problems have been studied by Bragg and Williams, Borlas, Fowler, Beta, and others. And here, Piles is referring to a number of different works which don't make a connection in terms of universality, but more the mathematical structure of a theory, this notion of a binary variable. So there was the notion of the so-called liberation rotation transition from Fowler. There was Beta's theories of alloys. All of these made reference to the Ising model. But the notion again that there was something like more universal here, this was still not recognized. So 1942, Onsager, had his career right across the quad from this point here. Onsager proved that the zero field, the existence of the zero field transition exactly gave an expression for the partition function. This is a epochal moment in many body physics. The Onsager revolution was just that. The proof that you could have a physical system and derive the partition function to show analyticities was very important in the context of what I've already told you, right? It wasn't understood that you could even get such a thing. Even then, though, the idea that the Ising model would be important and useful was still, I think, not appreciated. In 1952, Yang gave an exact formula for the magnetization. And the idea that that there was something kind of more deep and kind of beautiful physics lurking was still not appreciated. There's an anecdote from I believe a Christmas party at the Institute for Advanced Studies in the early 1950s, where Oppenheimer introduces Yang to some people at the Christmas party, saying something to the effect of, "You must come over here. You must come over here and meet Mr. Yang. He's done a marvelous bit of mathematics." And so what Yang had really done was write down an exact expression for the magnetization with an incredibly non-mean field exponent, right? This 1/8 exponent, which is about as different as you can imagine getting from mean field. So another epochal moment in many body physics, but brushed aside as a bunch of mathematics. So even Yang himself wrote in the late 1950s that the Ising model was of not physical, of no great physical significance because it wasn't, quote, realistic. And it was only really in the 60s and 70s that it was realized that simple models were important in their own right because they were evidence for phase transitions themselves, or let's say models for phase transitions themselves. Things like universal exponents, university classes, scaling, criticality, all of these kinds of things came out of the work of people like Wilson, Kadenoff, Fisher, Dahm, and Whittam, others, right? And it was realized eventually that the Ising model was important not because it was a particularly good model of ferromagnetism, which it wasn't, but that it was a good model of a phase transition itself, right? And maybe the simplest one we had. And so, right, so if the Ising model could be applied to, and you can get exact agreement with magnets, but also liquids and gases, binary alloys, then it has some realism to it, irrespective of the fact that the starting point may be irrealistic. Right? It's a model of the realism of phase transition, and this is certainly a beautiful thing. Okay, another Yale connection. Many of us learn about the subject of quantum phase transitions from Sachdev's book, which he wrote when he was a faculty here. This is my dog-eared copy of it, and Sachdev builds up the theory of quantum phase transitions from an analogy to the thermal transition and Ising chain in transverse field, which I'm going to come back to. So the history of the Ising model is mostly a history of classical physics, but the 1D Ising model is certainly the platform in which we build our understanding of quantum phase transitions on as well. The most remarkable results, of course, in the context of phase transitions is this notion of universalities, that phase transitions can be classified according to their exponents, that only the dimensionality of the order parameter and the dimensionality of space are the things that matter. And so in this regard, for instance, you can compare the phase diagram of the liquid gas phase transition, in particular, this critical endpoint as a function, let's say, of pressure and temperature, to the phase transition of is a 3D Ising model as a function of magnetic field and temperature, also with a critical endpoint. And if you focus on these regions at the end here, there's this kind of remarkable correspondence of exponents that with an appropriate matching from one set of variables to the other. And there's, of course, something very deep and beautiful about this, and this is why the theory of critical phenomena and experiments associated with it have, if you will, held the extended gaze of some of the smartest people of the last century. The Ising models are now, of course, everywhere. Of course, this is the magnetization, reduced magnetization as a function of reduced temperature for a layer of atomic iron. So a metallic system, very different than what Onsager had considered. But you see this remarkable agreement with the Onsager scaling form for magnetization over some 36 orders of magnitude of reduced magnetization and 24 orders of magnitude in reduced temperature. There are models for, let's say, lattice gas models and binary alloys that can be applied. Ising model has been applied in all different contexts to biophysics problems. Here's just one particular one that I pulled out about Ising models of cancer growth. The Ising model has been applied to social phenomena, for instance, studying phenomena of racial segregation in American cities. You can even find that Ising models of tax evasion. And so there are models here where you can use there are papers that explain how you can avoid paying your taxes using the Ising model. Okay. So what I want to do for the rest of the talk now, after that hopefully not overly long introduction, is, if you will, turn the clock back on all this progress. So I want to come back to Ising's original idea. He was considering a one-dimensional magnetic chain, and I'd like to ask, how can we realize Ising's model in a real material? So what would we want? We want it to be, let's say, 1D or quasi 1D. Spin 1/2, because we want the spins to be up or down. Maybe we would like small exchange constants so that we could perhaps manipulate the spins in the system with an external field. We would like it to be ferromagnetic. That's the case that Ising had originally considered. It doesn't have to be, but that would be the case most analogous. It needs to have strong Ising anisotropy, right? So spin generically would want to point in all 3 dimensions, but we want our spins to have a strong uniaxial anisotropy where the spins point up or down. And if it's going to be in the solid state, then we want to have no other kind of, if you will, competing interactions. We don't want to have lattice vibrations, phonons kind of get in the way and compete with the other interesting physics. And so it was pointed out some years ago, this material, cobalt niobate, columbite, as I already told you, you've seen this slide already, is perhaps the best material realization we have of Ising's model. And so this is kind of the form that we look at crystals. That's the naturally occurring form of it. But we're going to be looking and considering it, if you will, this zigzag chain that I can put right there of cobalt ions surrounded by oxygens sharing the edges of their octahedra in this fashion. And some of these details will be important as we go on. But at this point, let's just kind of abstract it. So cobalt is generally D7, 3D7. Cobalt +2 in this octahedral crystal field. It gives what we would say a high spin 3/2 and effective L = 1 moment. The details of this are not important, but effectively what goes into it is kind of a complicated local quantum mechanical object, which we can regard as a pseudospin, which either points up or points down. So let's put those, if you will, excuse me, spins in. And I want to get rid of the oxygens to just keep those guys along. It's a zigzag chain, and I can just consider, let's say, nearest neighbor interactions and pull it out straight, put the spins back in. It actually turns out in cobalt niobate that the spins actually lie in a funny direction, 31 degrees to the crystal axis. So they're there, but I can also imagine that I can just kind of do a uniform rotation of them and just put up. Let's get rid of the cobalts altogether, and that's the model that I had said, so the 1D Ising model. So that's how we're going to think about this. Excitations in the system generically would be spin flips, although we're going to see that there's some kind of wrinkles to that in a moment, right? Spin can be flipped up or down. The real material, cobalt niobate, is, as I said, the best material realization of the 1D Ising model. But there are some other interesting physics that are associated with it, and we're going to exploit that as we go. So as I take the system and I cool down, there start to be very, very strong one-dimensional correlations along the chain. And so you can see that here. This is a plot of the heat capacity as a function of temperature for both zinc niobate, which is a non-magnetic analog, and cobalt niobate. And as you cool down, it kind of comes down. This temperature dependence here is just the normal heat capacity that comes from the lattice vibrations in the system. And around 20 Kelvin, these two curves start to differ from each other. And when they start to separate, that's where I start to develop these one-dimensional correlations in the chain. And then you can see what happens is that there's a peak, it's a blow up right there, there's that peak, and then a little bump. And there's actually 2 low temperature phase transitions. You have these long ferromagnetic correlations. And then at 2 temperatures, there's two subsequent first order transitions that take you into a state at low temperatures, which are ferromagnetic chains, which are then anti-ferro coupled to their neighbors. And that's going to be important. So the first thing that's important is that before you get this long range ordered state, you have the correlation length along the chains is about 100 lattice constants. So it's almost a ferromagnetic chain. It's getting very long, and then blunk, you go through 2 first order transitions, and then you come into a state at low temperature, which looks, in the cartoon, looks roughly like this. 1D ferro chains, which have strong exchange coupling between them, and then weakly coupled to their neighbors in the anti-ferro fashion.
So what's the difference between zinc and cobalt?
Zinc is non-magnetic. So it's just the same thing. It's just a reference system, right? So we expect the phonons and whatnot are the same. So the difference is roughly the magnetic contribution, right? So if you took that, you subtracted them, you could then integrate C over T and get the entropy, for instance, and you would find, R log 2 per spin or something like that. It's the magnetic part. What's that? Well, that's just a blow up of the lowest part here, right? So that's up to 7 Kelvin. So that's just showing you here, there's 2 transitions, the peak and then this shoulder is another one. Yeah, exactly. Now, remember I said one of the things that we really want is to have strong anisotropy. And so you can see that here. So this is a plot of the magnetization as a function of temperature for a small magnetic field pointing in the A direction, the B direction, or the C direction. And so what you can see with the field pointing along A or C, the spins actually lie in the AC direction. So when I cool it down with a field in A or C, you have this spin and you can kind of cant it a little bit in A or C, depending upon which direction the field is. And the system magnetizes. The spins do cant in A or C. But they don't want to go in the B direction. B is a hard direction. We're going to want to put the field in the B direction eventually, but right now we're not. And what this shows you is that there's strong anisotropy in the system. It doesn't show you that there's strong Ising anisotropy, but it shows you that there's strong anisotropy, which is one of the things we want. Okay, so one more little bit of background here. So that's our, if you will, the Hamiltonian that Ising had considered. To understand this, we're going to actually have to add one more term to this Hamiltonian, and that's our Ising model or Ising model in transverse magnetic field. So that's the normal Ising term here. And then we're going to add a transverse field. And this term here has the form with this Sx. And Sx is a term in the Hamiltonian. And you can imagine if I take this guy, this 2x2 matrix, and I operate it on this, I get that. If I operate it on that, I get this. It's a spin flip term. So that's important. Magnetic field pointing in the x direction has the function of flipping spins. Okay. Now, so that's a cartoon of the material at low temperature on top. Ferromagnetically oriented spins, anti-ferro coupled to the neighbors. Now, one of the things that you learn in physics, and it's particularly true in spin systems, is that very often the naive variables that you're given are not the simplest variables to understand the system. And that's particularly true here. So we can focus on spin flips, for instance, for the excited states. But what I want you to focus on is not that so much, but instead these blue dots, which are the domain walls between regions of ferromagnetically oriented spins. Right? So I can, if you will, look at what I realized from this is if I kind of look at more and more spin flips, these spins, we cost energy at these domain walls. These spins here want to be anti-ferro coupled. And so there's a linearly increasing energy that goes up linearly in the separation of the blue dots. Now, if the system was pure Ising, that would be the end of the story. It would be uninteresting. We could figure out the energy of the excited states by just counting the distance between the blue dots, and that would be it right there. But it's not the end of the story. There are these terms which essentially look like spin flip terms, right? So in the language of spin flips, the spin flips are spin flips. But in the language of the blue dots, these domain walls, they're actually tunneling terms. So it's another way of saying kinetic energy, right? So if I flip this term spin here, it has the effect of tunneling the domain wall from one bond to the next. So I have 2 features here. I have this linearly confining potential between the domain walls, and then I have a kinetic energy term. And I can take this and I can map it to a one-dimensional Schrodinger equation in this form. So here I have a kinetic energy term. I have a linearly confining potential, right? So if this was x squared, we would solve this in terms of our old friends, the Hermite polynomials, but it's not x squared, it's x. So we have to solve it in terms of our new friends, a class of special functions called Airy functions. And so the energy eigenvalue structure has this particular form here, where there's some, let's say, constant plus some term here, z sub j, where the z sub j corresponds to the negative roots of the Airy functions. This was actually all first worked out for the Ising model in this article, 1978 of Physical Review D. Physical Review D is, for those of you who don't know already, is the particle physics journal for the American Physical Society. And people were interested in the Ising model for these kinds of confining potentials because this notion of the linearly confining potential between two domain walls has at least some superficial resemblance to the linear confining potential to two quarks in a meson. So we'll come back to this analogy.
So X is the length of the domain wall.
Yeah, yeah.
The first term is kinetic energy. Second term is string.
That's right. Yep.
So lambda is related to the exchange between the separate.
That's related to the interchain interaction. Yeah, in this model. Yeah, so we model that essentially as some kind of Weissmean field that comes from the effective field of the neighbors. But you could also imagine it's an applied field. You could also imagine if you had a truly 1D chain, you could apply a longitudinal field which breaks the degeneracy of spin up and spin down.
Right.
That would do it similar.
The kinetic energy comes from each term.
That comes from, so here I've kind of given you a cartoon version of it. In that cartoon version, it would come from the transverse field, SX. So it comes in, I'll talk a little bit about that. As far as this is concerned here, just imagine that there's some internal field which has the effective symmetry of an SX term.
Okay.
I think that's fine for now, but that's essentially what it is. So if it was just if it was truly an isolated 1D chain, we could apply an external field in the X direction. Here, there's an effective term, which I'll talk about a little bit later, which looks like that.
There are quantum states for the string, the chemistry spectrum.
Yep. Yep. Yeah. I'll show you. Yeah. Yeah. So what experiments? So I've given you a lot of preamble. So the kinds of experiments that we do in my group is what's called time domain terahertz spectroscopy. We do it in a variety of different forms. This is a version of one of our older spectrometers. I don't want to talk about the details of it too much. If you're interested, please ask questions. But the basic gist is that there is an ultrafast laser which creates pulses separated on the table. The laser comes in here and closes an optical switch, a semiconductor optical switch, which is biased. When it's closed, charge races across this gap in the semiconductor and jiggles on the scale of a picosecond, which is the electron hole recombination time. That jiggling of charge on picosecond timescales, the inverse of a picosecond is a terahertz. And so it's that jiggling of charge on this picosecond timescale, which creates this pulse of electromagnetic radiation, which goes off into space, let's say, interacts with a sample, which we might put there, and then is detected in kind of an inverse version of the generation process. The terahertz part of the electromagnetic spectrum was always very challenging to interrogate and characterize materials in. And the problem is that it's not that we don't have enough terahertz radiation, we have lots of it, right? We're awash in terahertz radiation right now. It's about being able to do spectroscopy in a sensitive fashion in the bath of black body radiation that we're living in. Usually when we look at materials with optics, we're typically coupling to electric dipole degrees of freedom. But if a material is, let's say, electrically uninteresting at low frequencies, it is an insulator and it has interesting magnetic degrees of freedom, then the time-varying magnetic field of the terahertz pulse can couple to magnetic dipole degrees of freedom, and it becomes a very, very sensitive way, high signal to noise way of doing various kinds of magnetic spectroscopy. And so we do a lot of this in my group. That's what data looks like here. So this is the electric field measured as a function of time. Here you see these look like echoes, and that's in fact exactly what they are. That is the light rattling around inside of samples. So we've transmitted a pulse through the material, and some of it makes it through, but some of it reflects inside. And there are multiple reflections of the light inside, and every time it kind of does a bounce, a little bit gets out. And so we need very good energy resolution, very good frequency resolution. So we have to scan out to really long times and then do the Fourier transform. That's what the spectrum looked like. So this is a plot of what is essentially the magnetic susceptibility as a function of frequency you see in the terahertz range or in the few millieV range. We take a sample and we cool it down to low temperatures. And you remember when I showed you the heat capacity curve, where the zinc niobate was separating from the cobalt niobate around 20 Kelvin. And that's what happens here. You basically see nothing, and you go up to around 20 Kelvin, and then the curve, this curve right here is 20 Kelvin. And then this peak, you get this kind of double peak feature, which looks roughly like a, let's say, joint density of states of a one-dimensional tight binding band. And then you hit this phase transition, and boom, all that sharp structure comes out. So, if you're like me, who have spent your career working on spectroscopy and condensed matter physics, you get very excited when you get curves like this, because we usually don't have such sharp structure. Peaks are broad generally in condensed matter physics. But there it is. There's the low temperature curve. So this is, again, susceptibility as a function of frequency in the terahertz range, also in the few millieV range. And there are a number of different peaks here. We call them M1, M2, M3, all the way up to M9. And then there's another guy here that we'll call 2M1. And then there's this big blob that I'll call the M1 plus M1 continuum. And so we can look at them and try to understand something about them. And so they're the lowest 9 peaks. So this is energy, millieV, versus some index, M1, M2, M3, all the way up to M9. And there is results of matching to the model of McCoy and Wu, who wrote down in 1978 in Physical Review D, this model basically for quark confinement, right? So you can fit the whole discrete spectrum just based on 2 free parameters. So, I think it's really quite remarkable, right? You have this kind of rich mathematical structure lurking in something that literally could have started as life blown out of a volcano. Okay. So, but there's other things, and what else is there as well? So there's this blob here at higher energies that we call the M1 plus M1 continuum. And this is where this quark analogy is useful. So we know we don't have such a thing as free quarks. If you have 2 quarks in a meson and you pull on them hard enough, you don't get free quarks, but you end up putting enough energy in that you pull new quarks out of the vacuum and you're left holding 2 mesons. And that's essentially what happens here as well. You hit an energy threshold, which is essentially 2 times M1, and you stop making peaks in this hierarchy, but now you can make 2 M1 particles, which are moving apart from each other with 0 center of mass momentum. Yeah. That would be 4 domain walls. Yep, exactly. Yep, exactly. This guy writes, one other thing with this right here, 2M1, we believe that is actually bound state of bound states. And so you can kind of see how such a thing might be possible, is that you could, and this is a cartoon of it, imagine you have, like, let's say 2 spin flips on one chain and 3 on the other. Well, these 2, there's some binding energy between them. And so this is a restatement of something you may know from, let's say, more elementary quantum mechanics, that every one-dimensional solution, one-dimensional potential, has at least one bound state. Attractive potential has at least one bound state. And so this is the bound state here of this kind of funny trapezoidal potential, this 2M1 peak. Okay. All right, good. So that was all interesting. My first, but it was essentially bonus, if you will. So my interest in this topic was because I was interested in quantum phase transitions. So quantum phase transitions are a phase transition that happens as a function of some non-thermal parameter. And the Ising model, as a function of some non-thermal parameter, for instance, the transverse field, is a simple model for quantum phase transitions. That's chapter 4 in Sachdev's book. I was in my office one afternoon. Thinking about the transverse field Ising model, as one does, and I got this email. Dear Dr. Armitage, enjoy these pictures of my father for your talk, Tom Ising, or Tom Ising, if you will. Tom Ising is a retired businessman living in Peoria, Illinois. He is the only son of Ernst Ising and Joanna Ising, which I'll tell you a little bit about their study. Is a kind of retirement hobby. He has a Google alert set up on his father's name, and follows the internet, if you will, for occurrences of the word Ising. And I was giving a talk some years ago at Berkeley on similar to this topic, and so he saw that I was giving this talk and followed up with this. I mean, it sounds funny, and it is. But it also, it was a remarkable thing for me when I got this email. It was like, these famous names in history. We forget sometimes, right? They're real people who, did their work, but then also left imprint on the world in different ways altogether. And so for me, it opened up this kind of remarkable correspondence that I really learned a lot about the history that wasn't directly related to the physics. So this is Ernst Ising. He was born in Cologne, Germany in 1900, and I think it's fair to say that the events of his life run parallel and through many of the major events of the 20th century. So he got his PhD in 1924, but was disappointed by his self-perceived failures at that time and decided to leave physics. He worked for a year in a patent office in Germany, but let's say with less success than other notable patent clerks around that time. Didn't like it, and he decided to become a teacher. Moved to Berlin in 1928 to study philosophy and teaching, and met a woman named Joanna Eimer, who was a doctoral student of economics. They got married in 1930. This is a picture of them on a camping trip in the Danube River in 1930. Ising taught in various German high schools until January of 1933, when Hitler came to power. And Ising was Jewish. And with the racial laws that were instituted, he went essentially unemployed for a year before finally getting a job in 1934 as a teacher for Jewish children in a secondary school, somewhere near Potsdam, outside of Berlin. This was the beginning of what Joanna Eimer, in her memoir, later called 12 Years on a Tightrope. The school expanded due to the increasing number of Jewish children. In 1937, he became headmaster of the school. That's a picture of him teaching there. I don't know why, wearing a white lab coat, looking particularly scientisty. I don't know why that picture was taken in this fashion, but this is him instructing children in mathematics. It was an experimental school, and so you can read about it. The article, Wikipedia article, quite extensive. It's in German. But it was an experimental school with the founder of the school was a woman named Feiertag, who was part of a kind of a school of thought that thought that schools for children had to be mixed with lots of art, right? Kind of similar to the Montessori movements around similar time. And a teacher had written about it that although, quote, terrible things were ongoing outside, inside was called a oasis in the desert. And another teacher described it as, quote, without syllabus, without state recognition, but with lots of freedom and music. Ising cared deeply about his teaching and his students, and also for them. And so Tom has told me that these children were Jewish, and many of them lost all of their families during the events of World War II. And a remaining father or parent figure that they had was this slightly older man who had taught them math and science, and many of them came to visit. This is a picture of Tom in New York City with one of the older survivors to it. I think, if I forget this woman's name, I apologize, but I believe she was the godmother for Tom Ising. They had So of course, the Nazi threat was ubiquitous in those years, and vandalism of the school and threats to the students were ever present. Ising and the founder of the school, Feiertag, repeatedly went to the local authorities and begged for protection. And they were always refused. Quote, the state has no reason to promote such facilities, and the application of the Jews are presumptuous. Quote, the terrible action by the community were dismissed on the ground that they were justified popular anger because the Jew home in Kaputh. Kaputh is the small town outside of Potsdam where this was. And so the teachers prepared for something terrible to happen. Betsy Rosenthal is the last surviving student of the school, and she had told that the students were taken for many walks in the woods behind the school, that they only later realized that this was basically preparing them for escape routes. November morning, 1938, this was the Kristallnacht. This was this pogrom against Jewish businesses and educational institutions in Germany. A crowd of 120 gathered outside the front of the school. They were delayed by the founder Feiertag, who later died in the concentration camps. And Ising and some of the other teachers took the students out the back. The school was destroyed and never reopened. January 27th, 1939, Ising was taken in by the Gestapo and interrogated for 4 hours, was eventually released under the stipulation that he leaves Germany. So he took his then pregnant wife. They tried to get themselves to the United States, but only made it as far as Luxembourg, where I think now, apropos of quotas that we have in the present day, they were basically refused entry for visas into the United States. They thought that they might be deported. They stayed in Luxembourg and thought that they might be deported for some period of time. Unbeknownst to them, in the Nazi bureaucracy, they had decided that the very last people to be deported to the camps were going to be Jewish men married to German women, and Jane Ising was German by birth, and so they essentially just outlived the war. He was one of only 36 Jews who survived the war in Luxembourg. In the spring, May, April of 1939, Tom was born and spent the first 8-9 years of his life in Luxembourg. And April 1947, they arrived in New York City, and Tom Ising was 7 years old. I've been interested to know, if you will, what did Ising know about the Ising model, right? So this is 1947. This is 23 years after his PhD thesis, 22 years after his only paper. This is after the Onsager Revolution, which Pauli had said was the only important physics that had happened during the war. Tom had told me that at various points when he went looking for a job, that Ising was asked, "Are you related to the famous Ising of the Ising model?" And Ising in later life had said it made it easier to look for a job when he was famous. It's actually not clear at all from the record when Ising actually learned about the Ising model. And I have a copy of his laboratory notebook, which is in the archives of Bradley University, which is where he ended up teaching physics. And it actually looks that it was actually in the early 1950s is when he actually understood that the name Ising was famous, and basically going back to the work he had done in those days, right? At that point, 10 years after the Onsager Revolution. In 1948, Ising became a professor of physics at Bradley University in Peoria, Illinois, where Tom Ising lives to this day. Ising's passion was teaching, and he would always say that a class had only gone well if the students had laughed at least once. He liked fine arts and poetry, and even till very late in life, he could recite classic German poems. And this was reflected in Ising's second publication, Goethe as a Physicist, which is here published in the American Journal of Physics in 1950. You can see here, Goethe as a Physicist, Bradley University, Peoria, Illinois, Ernst Ising. That's the second publication to his name in this article. So Goethe, the German man of letters, had some rather unconventional ideas about light and color and the perception of vision that were discussed in rather poetic language there, and of course, weren't entertained by Ising as being correct, but nevertheless of interesting significance. That is a picture of Ising teaching, as I mentioned. So that's one of these bicycle wheels that we use to demonstrate angular momentum. And this, I show it just because I find it amusing for reasons that I can't fathom. Somebody took the same picture and turned it into a spaghetti strainer here. So I posted without comment. In 1953, he got his US citizenship and presumably new names, right? Ernst Ising and Joanna Ising became Ernst Ising and Jane Ising. Sorry, Ernst became, let's say, the Isings became the Isings. In 1976, it was emeritus professor at Bradley University, and on May 11th, 1998, Ernest Ising died at the age of 98, having had a very long and productive life. For her part, Jane Ising taught economics and German in the public schools in Peoria and Bradley University. She founded the Planned Parenthood of Peoria, Illinois. She swam every day until her 100th birthday. And on the morning of February 2012, Jane Ising died on her 110th birthday. And Tom has told me that they had been planning on a birthday party, which they went ahead with anyway, which was a cake with 110 candles on it. That is Tom, his wife, the mayor of Mersch, Luxembourg, which is a small town in Luxembourg, Germany, where they survived the war. Hope to go there someday. The Rue Ernst Ising, physician. And this was in 2008 at the dedication of this street in Germany. Sorry, in this street in Luxembourg. Okay, so I have a lot more to say and not much time to say it. So if it's okay, I'll take 5 more minutes to tell you where we're going at with things now. So as I mentioned, I was in my office that afternoon thinking about the Ising model in transverse field. And the Ising model in transverse field is perhaps the simplest realization we have of a quantum phase transition. And so I want to give you a feeling of what we're doing with this. And there's a number of different things that come out, ideas like Kramers-Wannier duality, the Kitaev interactions, which are really still at the forefront of condensed matter physics. So mostly what I've told you about so far is, I made reference to things like quantum mechanics. It's largely, quantum mechanics has appeared in this context mostly in the form of quantization of spectrum, if you will. But when we think about a quantum phase transition, which is a change of the ground state of the system is a function of some non-thermal parameter, this is where quantum mechanics really manifests itself. In the case of the Ising model in transverse field, we know that there has to be a quantum phase transition. So if you imagine it's zero transverse field, the system is twofold degenerate, right? All the spins can be up or all the spins can be down. When I put a large transverse field on it, large enough field, the spins will all point in the field direction. And that's a singly degenerate ground state. And so I can't go from twofold degeneracy to single degeneracy without some kind of phase transition. And so there's a phase transition that happens at zero temperature that's associated with this ferromagnetic to what we refer to as quantum paramagnetic transition. In general, quantum phase transitions are characterized by a collapse of energy scales near the transition. There's a similar phenomenon in classical phase transitions called critical slowing down. Many quantum phase transitions, in fact, phase transitions in general, are also characterized by what we refer to as duality relations. So if I know something about the physics on one side of the system, one side of the transition, I can learn something about the physics on the other side by an appropriate change of variables, and that's true here. So in the case for, excuse me, there we go. So in the case of this quantum phase transition, so if that's my Hamiltonian here, so my Ising interactions and the transverse field interaction, the excitations on the ferro side are these domain walls, as we talked about. When we come in with a neutron, let's say, or a photon, and we're going to excite the system, we always have to make two at a time of these. And they can be bound together in the fashion that I already told you about. But the elementary excitations themselves are these domain walls. That's different from the other side of the transition, where the elementary excitations are just spin flips. Now, this duality relation, which in this context is referred to as Kramers-Wannier duality, appears in the fact that if I was to ask, let's say, for some particular transverse field G, the gap to make one of these is 2J times 1 minus G. And if I was to consider, let's say, a similar distance on the other side of the transition, I get a very similar relation, 2J times 1 minus G. Now, the difference is between the ferro side and the para side is that I have to make two of these on the ferro side and only one on the para side. They're both the elementary excitations of the system, but there's this factor of 2. And that actually shows up in the spectrum itself. So we're looking, for universal numbers here. And so there's a universal factor of 2 in the excitation spectrum. This is a plot of the absorption of the system as a function of frequency in the terahertz range. It looks a little bit different than the data I was showing you earlier because this was taken in a different system. This is zero field at the bottom down here. And that's the spectrum that I've already told you about. We put a transverse field on it, and there's a few things that happen. But the thing that I want to point out mostly is that there's this lowest energy peak that comes down towards zero and then comes back up there. So the annals of condensed matter physics are full of people trying to, if you will, infer the existence of a quantum phase transition between some kind of collapse of data like DC resistivity or susceptibility or something. When they're doing that, really what they're trying to do is to infer this energy scale, which collapses near the quantum phase transition. So we don't have to do that at all. We can just read it off from the spectrum. We can just see how the energy scale collapses and comes down on one side and then comes back up on the other. And if I plot this lowest energy feature, that's here, the energy of the system, it kind of comes up, and I'll talk about that in a second. But I want to point out here is it comes down and comes back up. And these two dashed lines, they differ by the slope of 2. So another universal thing, there's a factor of universal integer, factor of 2 hiding in this system, again, in this material, which could have started its life blown out of a volcano. Now, the other thing that comes into this, and let me just say one more quick thing, is what you can see is the other thing that happens is when we first put the transverse field on it, there's this kind of narrowing of the spectrum. It actually comes up in the beginning before it goes down. And that's reflected here, right? There's this narrowing of the spectrum, and it comes up, the spectrum gets narrower, and then it comes down. And this is something that I was very puzzled by, didn't quite understand how to make progress, and it was the end of my colloquium some years ago before I finished it at the University of Kentucky and discussed with Ribu Call, and we got to talking and worked it out basically in about 20 minutes. And it has to do with some features that I had neglected to kind of emphasize early on. One of the things I had said was that these octahedra are edge-sharing octahedra. And this leads to a very natural orientation of the Ising axis in the system, which flip-flops its Ising anisotropy from bond to bond in the system. This is an interaction that in its modern context is called the Kitaev interaction. Kitaev had postulated a version of a quantum spin liquid on a two-dimensional hexagonal lattice where we have 3 different directions for Ising interactions. And here we just have 2 because it's a 1D chain. I'll just say that there's kind of let's just kind of rush through this. The local axis alternates sign from bond to bond. And this gets a little bit back to what Leonid was asking. It has the effective form of a transverse field, which looks like this, where Hx, if you will, is an external transverse field. And then there's an internal transverse field, which depends on the twist angle and also changes sign from bond to bond. So what happens when we put an external field on? There are positive bonds and negative bonds. I put, let's say, a positive field on. Some bonds go up and some bonds go back to 0. If this was all that was going on, there would be some exceptional field where the system would just split up into dimers. Of course, there are other terms, but you get these. This is the narrowing of the bandwidth. So this is the first, I think, definitive evidence for interactions of the Kitaev type, which has been postulated to be important for the realization in two-dimensional systems for quantum spin liquids. Okay, I'm out of time. I told you I would be. I'll leave the last words to Ising himself. This is from Ising's second paper, Goda as a physicist in the American Journal of Physics in 1950. Ising wrote, Goda's approach to science was that of an artist who thought he could conceive the secrets of nature in all their complexity. He was convinced that translation into the language of mathematics was a distortion of reality. And so I don't think anybody in the room here today believes that translation into mathematics is a distortion of reality. But I think what we see, in fact, is there's something very beautiful with realizing perfect exponents, near magnetization transitions, special mathematical functions like Airy functions appearing in the excitation spectra of this small rock, if you will, that could have started its life blown out of a volcano. And so I'll just finish there. You've seen my conclusions already, and I thank you for your attention.
Thank you, Peter, for a very insightful talk. Questions? Bring the microphone for you.
Just comment. Einstein, you probably know Einstein had a summer home in Kaput, which you mentioned Ising, that still exists today. And I don't remember the dates he was there, but I think 1933 comes to mind.
So there are all kinds of anecdotes here, and one of the ones that I don't tell was that when Einstein left for the United States in 33-ish, the house that was given to Ising and his wife, Joanna, became Jane, didn't have a bathtub. And it was right next door to Einstein's house. And they somehow arranged that they could use the bathtub in Einstein's house. So, yeah, lots of anecdotes, not room for them all, but thank you, yes. Yeah, right next door.
There questions?
Hey, thanks for a great talk. So in the continuum model of linearly confined quarks, this is the meson, you showed really nice agreement with 2 fitting parameters to the eigenvalues, the energies. How does it? Can you calculate the oscillator strength of each one, the matrix elements, to be created by the terahertz?
Yeah. So
does it work?
So we haven't. So that's a good point. We haven't actually worked that out. It is qualitatively close. And so let me show you what we have done here that a little bit answers your question. So that spectrum is so rich that we can basically do what atomic physicists do, and we measure spectra, and with some knowledge of the system, we can figure out wave functions. And so these states, these domain walls, are, I've presented them as a cartoon that it's like, let's say, 3 flip spins wide, but the reality is they're actually quantum mechanical superpositions of, they're not states they're not spin eigenstates. So we should think of them as superpositions of different numbers of spin flips. And so that's the wave functions there on the right. as fitted from the spectrum. And so I didn't do a quantitative measure, what you can see here, right? So the M1 state is a little bit of one spin flip mixed in with a little bit more of two, a little bit less of three. As you get up to very one higher spin, M's values, you see this oscillation. That's the area function solution kind of coming out.
You can see it peak near the classical turning point, right?
That's exactly right. And this here, if you will, the intensity we see it in the spectrum. When we excite the system, we do it with the magnetic dipole operator, and what it physically does is it flips a single spin, and then the strength we see is how it projects onto these states. And so it's, I don't know how exact it is, but it's roughly consistent with that, right? The peak intensities are going down in some fashion. It would be interesting to look at it in more detail. Yeah, thanks.
Anyone else? Okay, I think in the interest of time, we'll just thank Peter again.
Okay.
Thanks.
Yeah.